Now, the magnitude of a vector is just its length. When we say magnitude, let's talk about vector v here, and I'll use the half arrow notation. Vector v has magnitude, and we write vector v either with a single sort of absolute value symbol either side of the v, or oftentimes you'll see it with double. The difference, I think, is primarily to distinguish the idea of absolute value. Numbers can have absolute value. We talk about the absolute value of -3 is 3. But in terms of vectors, we are talking about its length specifically. So you will see both of these notations. Our textbook uses the double absolute value symbol to indicate magnitude. And so I'll stick with that throughout the rest of these videos, but be aware that sometimes you do see the single, and basically it's a matter of context. If you're talking about vectors and you see this symbol, then what they mean is the magnitude of the vector. The magnitude of the vector is just its length. And there are lots of places where we'll need to know what the magnitude of a vector is. Places where we'll need to determine what that magnitude is, either in specific terms or in general terms. And it's actually really straightforward. In R2, if we have a vector in, let's see, I'll use a different color for the vector. If we have a vector, I'm going to draw my vector over here initially, and then I'm going to grab it and move it to use the right tool. If I have a vector floating in space like this, and we've talked about this before, I can take that vector and move it so that its tail, or its initial point, is at the origin. And notice the length of the vector doesn't change at all if I move it around. So if I choose to put it here at the origin, or so that its tail is at the origin, then I can use the Pythagorean theorem to figure out what the length of the vector is. I have to know what the terminal point is, or what the 2 points that make up the vector are. But let's say that this vector has the terminal point of this vector is maybe 4, 3. That's that point. Well, that means that in order to arrive at that point, I've had to go out 4 and up 3. And what I've got here is a right triangle. So using the Pythagorean theorem, I'm going to call the length of this vector d, the third side of my right triangle, the hypotenuse. I'm going to say that d squared is equal to, in this case, 3 squared plus 4 squared. And that's 9 plus 16. And that's, when I add those together, 25. So d must be plus or minus 5, but since we're dealing with a length, it's positive. So d is 5. And literally all I've done here is use the Pythagorean theorem to find the hypotenuse of a right triangle. I could also have done it this way. I could say, since d squared is equal to 3 squared plus 4 squared, d is equal to the square root of 3 squared plus 4 squared. This, of course, is 9 plus 16, which is 25, and the square root of 25 is still 5. So the point is that to find the length of a vector, I've just used the Pythagorean theorem. So let's write down, I guess it's kind of our first formula, the length of vector v. Actually, let me back up. Let's say that we have a vector v that, if I put it in standard form, has x-coordinate v1 and y-coordinate v2, then the length of vector v, the magnitude of length of vector v, is going to be the square root of v1 squared plus v2 squared. It's just that simple. So let's say I have a vector u that is at 9, 3, which on a graph, actually let's go ahead and use a negative here, 9, -3. On a graph would look something like this. It's just a quick sketch, so it's not going to be super accurate. I have to go to the right 9 and down 3, so I'm going to end up with a vector that sort of looks maybe something like that. What is the length of that vector? Well, if if I had to go out 9 and down 3, then using the Pythagorean theorem, I get the square root of u sub 1, which is 9 squared, plus u sub 2, which is negative 3 squared. That will be the square root of 81 plus 9, which is the square root of 90, which simplifies to 3 root 10. And that's it. That is the length of vector u, if vector u is this vector. Just like if vector v is this vector, and I used point notation here because I was talking about, when I set this up, I was talking about getting to that point. Well, that point is the terminal point of the vector, and I'm looking for the magnitude of the vector, which is the length of the third side, right? So it's just the Pythagorean theorem. Now, if I'm in 3 dimensions, it's a little bit different, but the formula turns out to be pretty much the same. I'll start with that. I'm going to say let vector v equal v1, v2, v3. I'm using this notation in much the same way as I used x1, x2, x3, and so on. I used that notation when I was talking about matrices. And that's primarily because I don't know what dimension my vector might end up having, and if it's got a large enough dimension, if I'm talking about, 17 or even 27, then I'm going to run out of letters of the alphabet before I, account for all of my dimensions. So I'm using v sub 1, v sub 2, v sub 3 just to kind of, for consistency's sake, and so that I don't run out of letters. So I've got my vector v here, and I'm going to say let vector v be that. Then if that's the case, then the magnitude of vector v is equal to the square root of v1 squared plus v2 squared plus v3 squared. It's really just that simple. The question maybe now arises, why does that work? Well, if we're in 3 dimensions, then we might have a coordinate system that looks something like this. Hopefully you can see that this looks something like the corner of a room, right? This is the where the 2 walls meet, and this is where the floor meets the one wall, and this is where the floor meets the other wall. If I have a vector in 3 dimensions, then let's see, it might look something like this. And it's likely I've had to go out x, along y. Let me try that one again. Along y, that's better, and up z to get to the terminal point. So I have, this is my v1 coordinate, this accounts for my v2 coordinate, and this accounts for my v3 coordinate. And there's no triangle here. The sort of the shape that I'm looking at, the shape that I'm looking at is like a bent sheet, right? It's like a piece of paper that's twisted. So at first glance, it doesn't necessarily look like I'm going to be able to use the Pythagorean theorem here, but I am. What I'll do is I'll first figure out, let's see, I'll use a different color again. I'll first figure out what the length of this line segment is, because that line segment is the hypotenuse of this triangle, one that's kind of on the floor here. And once I know that, I'll be able to take a look at this triangle that's kind of floating in space, and that's also a right triangle. So what I've done is I've kind of creased the paper, as it were, and I'm going to use the length of the yellow line segment as a leg. That's a hypotenuse. It's the hypotenuse of this triangle on the floor down here, but when it's looked at as part of the triangle that's floating in the air, that it's a leg, right? It's a leg of this other triangle. So I'll add my little right angle marks here and here. And I can say, let's call this yellow line segment Y, because Y for yellow. The length of that line segment is, I mean, it could be a vector, right? But it doesn't necessarily have to be a vector. It's just a line segment. It is going to have, by the Pythagorean theorem, the magnitude v1 squared plus v2 squared. That is the length of the line segment y. What I really want, though, is the line segment of this vector here, which is this pink vector, right? So I'm going to, let's give that, does that have a name? Yes, I called that vector v. So that's vector v. Vector v has magnitude the length of this line segment squared plus the length of this line segment squared. So let's write the square root of the length of the yellow line squared plus v3 squared. But the length of the yellow line we determined up here. It's this thing right here. So I'm going to write that in now. It's the square root of v1 squared plus v2 squared. And what happens when you square a square root? Those two things cancel. And so what I have for the magnitude of my vector v is the square root of v1 squared plus v2 squared. No square root anymore because I squared that term essentially, and that squaring took the square root away. And then I still have plus v3 squared. So the length of vector v, if I know the coordinates of its terminal point, or if I have its name in component form like this, is just the square root of v1 squared plus v2 squared plus v3 squared, depending on what those values are. So there's my formula here. For a vector v, v1, v2, v3, its magnitude is given by the square root of the squares of the sides. The squares of the components. I'll just do a quick example. Let's find u is vector 3, -1, -2. The magnitude of vector u is just the square root of 3 squared plus -1 squared plus -2 squared, which is the square root of 9 plus 1 plus 4. That's 14. So I get the magnitude of vector u equals the square root of 14. That doesn't simplify. I have a factor of 2 and a factor of 7. I can't simplify that. So that's an example of how to find the magnitude of a vector in 3 dimensions.